On July 1st, 2025, while most of humanity was gearing up for summer vacations and not thinking about cosmic mysteries, the Atlas telescope in the Chilean Andes picked up something unusual, a faint speck of light moving along a trajectory that didn't fit the familiar orbits of our solar system. Astronomers huddled over their screens, checking the calculations again and again, because the numbers were telling them something incredible. This comet didn't come from the Kuiper belt, not from the Oort cloud, but from interstellar space, the third interstellar visitor in recorded history. They named it 3I Atlas, and from day one, it started throwing surprises at us. Drop a comment and let me know where you're watching from and what time it is for you right now. I want to know who's joining me on this journey. A green coma wrapped around 3I Atlas's nucleus like a glowing shroud. This green glow, the result of diatomic carbon molecules breaking down under sunlight, gave the comet an almost mystical appearance in the photos that started appearing in scientific journals. The comet's shape turned out to be elongated, oblong, like an ancient spindle weaving invisible threads between the stars. Scientists quickly realized they had a unique opportunity in front of them: to study material that had traveled through interstellar emptiness for millions, maybe billions of years, carrying within it memories of other suns, other planetary systems. But the real surprise was still ahead. When astronomers calculated 3I Atlas's trajectory, they discovered something that seemed like an almost impossible coincidence. The comet was going to pass perihelion, its closest point to the Sun, in late October 2025. And at that exact time, in that exact region of space, two Earth spacecraft heading to their distant destinations were supposed to be passing through. It was as if the universe itself had arranged a meeting that no one had planned. The Hera spacecraft, a creation of the European Space Agency, was completing the first stage of its long journey to the asteroid Didymos. This mission is part of a grand planetary defense experiment. Back in the fall of 2022, the American spacecraft DART deliberately crashed into Dimorphos, a small asteroid and moon of Didymos, trying to change its orbit. It was the first test of technology to protect Earth from dangerous asteroids. Hera was sent to study the aftermath of that impact, measure the crater, understand how effective the maneuver was. But now, moving through the inner solar system, Hera was going to find itself in the path of something completely different, in the path of a comet from interstellar darkness. Europa Clipper, NASA's massive spacecraft weighing nearly 6 tons, was heading to Jupiter's moon Europa. Beneath the thick, icy crust of this celestial body lies a global ocean of liquid water, possibly containing more water than all of Earth's oceans combined. Scientists hope to find signs of life there, or at least conditions suitable for its existence. Clipper is equipped with the most advanced scientific instruments: radars to peer through the ice, spectrometers to analyze composition, magnetometers to study the subsurface ocean through its magnetic field. No one thought these instruments would come in handy before even reaching Europa, in a completely unexpected situation. When a comet approaches the Sun, an ancient cosmic dance begins. Ice on the nucleus surface starts to vaporize. First water ice, then frozen gases, carbon dioxide, methane, ammonia. These vapors burst into space, carrying dust particles with them, creating a visible coma around the nucleus. But the solar wind, a stream of charged particles rushing from the Sun at hundreds of kilometers per second, does something even more impressive. It ionizes the gases, turning them into plasma, and carries this plasma away from the Sun, stretching out a long, ghostly, glowing ion tail behind the comet. This tail can stretch for millions of kilometers, sometimes crossing the orbits of several planets at once. It's not a solid structure, but rather a tube of rarefied plasma, threaded with magnetic fields, filled with charged particles, ions of hydrogen, oxygen, carbon, nitrogen. Everything that made up the comet in its home star system is now dispersing in this glowing trail. And it's through this trail, through this plasma river of interstellar matter, that Hera and Europa Clipper were supposed to pass. Scientists quickly calculated the time windows. Hera would enter the potential intersection zone with 3I Atlas's ion tail between October 25th and November 1st, 2025. Europa Clipper would follow, its window stretching from October 30th to November 6th. 6 days, maybe 7, when Earth's instruments could taste material from another star system without changing course, without spending precious fuel, simply by turning on the instruments at the right moment and recording data. This was a stroke of luck that couldn't be missed. Normally, to study a comet, you need to send a dedicated mission, spend years preparing, billions of dollars on development and launch. Remember the Rosetta mission. It took 10 years to reach Comet Churyumov-Gerasimenko to study it up close. But here, 2 spacecraft heading to completely different destinations were getting a free bonus, the chance to touch the mystery of interstellar matter just by being in the right place at the right time. But what exactly could be learned from this chance encounter? Magnetometers on both spacecraft could detect disturbances in the solar wind caused by cometary material. Particle detectors could count ions, determine their energy and velocity. Spectrometers could reveal the chemical composition. How much hydrogen, carbon, oxygen is in the comet? What molecules are present? Isotope analysis could tell us about the origin of the ice, whether it was born in a cold molecular cloud or in a protoplanetary disk around a young star. Organic molecules were of particular interest. Comets often contain complex organics, precursors to life. Did 3I Atlas have amino acids, the building blocks of proteins? Did it have nucleobases that make up DNA? If so, did that mean life isn't a unique phenomenon to Earth, but something common in space, something that travels between stars on comets? These questions excited not just scientists, but everyone following the developments, everyone who thought about our place in the universe. The James Webb Space Telescope had already pointed its infrared mirrors at 3I Atlas and detected signs of water vapor and carbon dioxide in its spectrum. But the ratio of these substances was unusual, not like comets from the Oort cloud. This hinted that conditions in the star system where the comet was born might have been different from conditions around our sun. The flyby of Hera and Europa Clipper through the ion tail could confirm or refute this data, add details impossible to see from a distance. And here's where the story takes on a shade of mystery that those who look for something more than just physical phenomena in space love so much, because the coincidence seemed too perfect. A comet from interstellar space appearing exactly when 2 Earth spacecraft are on the right trajectories. The geometry of orbits aligning so precisely, as if someone had specifically calculated the meeting. Some began asking questions. What if this isn't a coincidence? What if 3I Atlas isn't just a comet, but something more? A message? A probe? A sign? Of course, scientists smiled at such suggestions. The probability of a random coincidence, they said, isn't so small that you need to look for mystical meaning in it. Space is huge. There are many objects. Trajectories intersect constantly. But those who wanted to believe in mystery found their arguments. The green coma, a color that in Earth cultures is often associated with something otherworldly, alien. The elongated shape of the nucleus, similar to the legendary Oumuamua, the first detected interstellar object, about which people still debate whether it was just an asteroid or something created by intelligence. The story of 3I Atlas was just beginning. October 2025 was approaching, and with each day the comet grew brighter, approaching the sun. Its ion tail was growing, stretching away from the star, preparing to embrace Earth's visitors. The mission teams of Hera and Europa Clipper were preparing their instruments, checking software, planning what data to collect and when. All of humanity, holding its breath, awaited the meeting that was supposed to happen at the boundary of the known and unknown, between the routine of space flights and the mystery of interstellar vastness. On October 3rd, 2025, 3I Atlas swept past Mars at a distance of just 19 million kilometers. The red planet, frozen and silent, became the first witness to the interstellar visitor's approach to the inner solar system. European and Chinese Mars probes tried to point their instruments at the passing comet, but the distance was too great for detailed study. However, this close approach served as a reminder. The clock was ticking, and the real encounter wasn't far off. Scientists knew time was working against them. On October 29th, the comet would reach perihelion, its closest point to the Sun, just 126 million kilometers away, between the orbits of Earth and Mars. This is when the comet's activity would peak. Solar radiation would vaporize ice at a furious rate, throwing tons of material into space every second. The solar wind, accelerated to 300 kilometers per second, would slam into this cloud of gas and turn it into a plasma river stretched millions of kilometers away from the Sun. It's through this river, through this ghostly trail of interstellar matter, that Earth's messengers were supposed to pass. But there was a question that kept engineers and scientists awake at night. Were their spacecraft even ready for such an unexpected task? After all, both Hera and Europa Clipper were built for completely different purposes, their instruments tuned to completely different objects of study. No one had built into the designs the ability to analyze cometary material. Europa Clipper turned out to be the lucky winner in this lottery. Among its 9 scientific instruments were 2 that seemed almost specifically designed for studying ion tails. The first, the Europa Clipper magnetometer, or ECM for short, was an array of 3 sensors on an 8-meter boom, capable of detecting the tiniest changes in magnetic fields. The second, the Plasma Instrument for Magnetic Sounding, or PIMS, consisted of 4 Faraday cups placed on opposite sides of the spacecraft, ready to catch charged particles and determine their energy, velocity, and direction of movement. These instruments were created to study Europa's subsurface ocean. The idea was brilliantly simple. Jupiter's magnetic field, one of the most powerful in the solar system, constantly changes due to the giant planet's rotation. These changes induce electric currents in the salty water beneath the moon's icy crust, and the currents generate their own magnetic field. By measuring this secondary field, you can determine the ocean's depth, its salinity, the thickness of ice above it. But the same sensors that were supposed to sense magnetic waves from Europa's ocean could easily detect disturbances caused by cometary ions. PIMS worked on an elegant principle. Charged particles would fly into a Faraday cup, pass through a modulated grid under high voltage, and strike segmented collector plates. From the current distribution between segments, you could determine the plasma flow direction, from the current magnitude, its density, from the energy needed to overcome the grid barrier, the temperature and velocity of the particles. If Europa Clipper passes through 3I Atlas's ion tail, PIMS would register a spike in charged particles of unusual composition, not solar wind, but interstellar matter, ionized and carried away from the cometary nucleus. The situation with Hera was sadder. The European spacecraft carried a magnificent set of instruments for studying asteroids, but not one of them was designed to detect ions or magnetic fields. The asteroid framing camera, a pair of high-resolution monochrome cameras capable of shooting invisible light. The thermal infrared imager, a Japanese-made thermal camera, an heir to instruments from the Hayabusa 2 mission, measuring surface temperature and thermal inertia. Hyperscout H, a hyperspectral camera working in 25 spectral bands, from visible to near infrared, determining mineral composition. A laser rangefinder, precisely measuring distance to target. All these instruments were useless for studying the rarefied plasma of a comet's tail. The cameras would see practically nothing. An ion tail is too diffuse to photograph up close, paradoxically visible only from a distance, when millions of kilometers of glowing plasma combine into a single picture. The spectrometer could theoretically detect emission lines from ions if their concentration was high enough, but calculations showed that at a distance of 8 million kilometers from the tail's central axis, the chances were practically zero. Hera would pass through interstellar matter, but remain blind to it. 8 million kilometers. That's exactly how far from the central axis of the ion tail both spacecraft were supposed to pass, according to calculations using the tailcatcher model. This computer program, developed specifically for predicting comet tail geometry, took into account solar wind speed, comet sublimation intensity, magnetic fields, radiation pressure. It drew an invisible tube of plasma stretching from 3I Atlas's nucleus away from the Sun, bending under the influence of the comet's orbital motion and variable solar wind flows. 8 million kilometers sounded like a huge distance, more than 20 times the distance from Earth to the Moon. But for a comet tail, this was the periphery, the outer boundary where plasma was already mixing with ordinary solar wind, losing its identity. In 1996, Comet Hyakutake passed by the Ulysses spacecraft, and its ion tail was detected at a distance of more than 3 astronomical units from the nucleus, nearly 500 million kilometers. Material sublimated from the comet traveled through the solar system for weeks, dispersing but remaining chemically recognizable. This gave hope. Even on the periphery, even in a rarefied region, Europa Clipper's sensitive instruments could pick up the signal. The magnetometer would detect distortion of field lines, an effect called magnetic draping, when the solar wind's field flows around an obstacle in the form of a cometary atmosphere, folding like fabric around a stone in a stream. PIMS would register a change in plasma composition. Instead of the usual protons and electrons of solar wind, there would be ions of water, carbon dioxide, methane, cyanide compounds, all the richness that made up the body of the interstellar comet. But the problem wasn't just distance. The problem was the unpredictability of the solar wind. This plasma river flowing from the sun wasn't constant and calm. Its speed varied from 200 to 800 kilometers per second. Its density fluctuated by factors of 10. Coronal mass ejections, giant bubbles of plasma bursting from the solar atmosphere, periodically pierced interplanetary space, crushing and distorting everything in their path. The comet tail's geometry depended on these parameters, and predicting it in advance to within 1 million kilometers was impossible. The tailcatcher model could only give approximate time windows. For Hera, October 25th to November 1st. For Europa Clipper, October 30th to November 6th. 7 days of uncertainty for each spacecraft. 7 days during which somewhere out there, in the emptiness of space, their trajectories might cross the invisible trail of an interstellar traveler, or not cross it. If the solar wind turned out weaker or stronger than expected, if the comet didn't sublimate as actively as models predicted, if thousands of other variables didn't align the way scientists calculated. And here's where the human factor entered the story. Europa Clipper was managed from NASA's Jet Propulsion Laboratory in Pasadena, California. In the fall of 2025, the laboratory was going through tough times. Internal restructuring had led to the layoff of 550 employees. The mission team was overloaded with main tasks related to navigation and preparation for arrival in the Jupiter system. Adding comet tail observations on top of the program meant extra work, extra risks, extra expenditure of the spacecraft's resources. No one knew whether engineers and scientists would decide to turn on PIMS and the magnetometer at the critical moment. No one knew whether they'd manage to receive information about this scientific opportunity in time. Published in a preprint version of a paper on Archive by two researchers, Samuel Grand from the Finnish Meteorological Institute and Geraint Jones from the European Space Agency. These two calculated the encounter geometry, wrote a short note for research notes of the American Astronomical Society, posted it in open access, and waited to see if their message would reach those who make decisions. The situation resembled a cosmic version of telephone. Scientists knew about the opportunity, but didn't control the spacecraft directly. Engineers controlled the spacecraft, but were busy with standard operations. Information had to pass through a chain, from astronomers to mission specialists, from specialists to project managers, from managers to operators, from operators to commands uploaded into onboard computer memory. And all this had to happen in a matter of days, because the time windows were narrow and closing fast. Meanwhile, the comet continued its journey toward the sun, not knowing and not caring about human plans and problems. Its green coma grew, enveloping the nucleus in a glow of diatomic carbon. Its ion tail stretched out, preparing to receive or pass by Earth's visitors. October 29th was approaching, and with each day it became clearer. This encounter would either be a triumph of improvisation and scientific daring, or a missed opportunity that would be regretted for decades. Because when else would such a coincidence happen? An interstellar comet and two spacecraft in the right place at the right time. On July 21st, 2025, the Hubble Space Telescope turned its mirrors toward 3I Atlas. The comet was 447 million kilometers from Earth, farther than Mars, closer than Jupiter, and looked like a faint, reddish spot wrapped in a hazy glow. The color was unusual. Comets are usually white or bluish, reflecting sunlight through water vapor and dust. But 3I Atlas glowed red, like an ancient fire lost in cosmic darkness. This reddish tint linked it to the legendary Oumuamua, the first interstellar object discovered in October 2017. Oumuamua swept through the inner solar system like a ghost, showing no coma, no tail, leaving behind only debates. Was it an asteroid, a comet, or something created by intelligence? Harvard astrophysicist Avi Loeb proposed a hypothesis about artificial origin, about a solar sail from an alien probe. Most scientists rejected the idea, but seeds of doubt were planted, and now, when 3I Atlas appeared with a similar color, those doubts sprouted anew. Spectral analysis showed the red color came from the nucleus surface, or from inner layers of the coma. This indicated the presence of complex organic molecules, tholins, polymers formed under cosmic radiation over millions of years of interstellar wandering. Such molecules darken and redden over time, like wood in the sun. This meant 3I Atlas was old, very old, and had traveled between stars for a long time before fate brought it to our solar system. In August, the James Webb Space Telescope aimed its infrared spectrograph NIR speck at the comet. This instrument can break light into components and determine which molecules emit or absorb it. The results puzzled the scientific community. In 3I Atlas's coma, they found an incredible amount of carbon dioxide, 6, and by some accounts 8 times more than water. For comparison, solar system comets usually consist predominantly of water ice, with carbon dioxide playing a secondary role. Here, the proportions were completely flipped. This discovery raised questions about the comet's birthplace. Carbon dioxide dominates in regions of protoplanetary disks located close to the so-called snow line, the boundary beyond which temperature drops low enough for gases to freeze. If 3I Atlas formed near such a boundary in its home star system, that would explain the excess carbon dioxide. But then another question arose. How did a comet born close to a star manage to escape gravitational captivity and set off on an interstellar journey? A catalyst was needed, a gravitational slingshot from a giant planet, a close passage of another star, some dramatic event in that system's youth. The Swift telescope, NASA's orbital observatory designed to study gamma-ray bursts, also pointed its detectors at 3I Atlas. And here, a strangeness occurred. Swift's data contradicted Webb's. Instead of excess carbon dioxide, Swift registered intense release of water vapor at a distance of 3.5 astronomical units from the Sun. Too far, too cold for such activity, if the comet consists predominantly of water ice. This discrepancy made scientists wonder, maybe the comet is heterogeneous? Maybe different sections of its nucleus sublimate differently, creating contradictory data depending on which side faces the observer. In late August through early September 2025, the Very Large Telescope in Chile began a series of observations of 3I Atlas using an ultraviolet Echelle spectrograph. Scientists were looking for metal lines in the coma spectrum, iron and nickel. These elements are regularly detected in cometary Comet, though their presence there seems paradoxical. The temperature on comet surfaces is too low for sublimation of silicates or sulfides, the forms in which these metals should exist. So where do they come from in the gas cloud around the nucleus? With 3I Atlas, something unprecedented happened. At a distance of 3.14 astronomical units from the Sun, a nickel line appeared in the spectrum. But there was no iron, none at all. The comet approached the Sun. Solar radiation intensified, temperature rose, and only when the distance decreased to 2.64 astronomical units did iron lines finally appear in the spectrum. Nickel was sublimating at lower temperatures than iron, the complete opposite of what should happen according to standard physics. The ratio of nickel to iron in the coma turned out to be tens of times higher than any other known comet. Moreover, this ratio changed rapidly as it approached the Sun. First, there was only nickel, then iron began appearing. The balance shifted, but remained anomalous. No previous study had recorded such dramatic changes. Even with Comet Borisov, the second interstellar visitor discovered in 2019, the metal ratio was stable and similar to solar system comets. Astronomers proposed a radical explanation. Perhaps inside 3I Atlas's nucleus, nickel carbonyl is forming, a volatile organometallic compound with the formula NiCO4. On Earth, this process is used in industry for nickel purification, or is heated in carbon monoxide atmosphere. Nickel forms a volatile compound that evaporates. Then it's decomposed back to get pure metal. But for this to happen naturally in a comet, very specific conditions are needed. Presence of nickel grains, carbon monoxide, certain temperature and pressure. If this hypothesis is correct, then Comet 3I Atlas is a chemical laboratory where processes never before observed in natural space conditions are taking place. This opened fascinating prospects. How many other unknown chemical reactions might occur in interstellar objects? What exotic compounds can form in the depths of comets traveling millions of years in cold and darkness? Could interstellar space be not a dead void, but a giant chemical factory producing complex molecules that then scatter across the galaxy, seeding planetary systems with building blocks of life. The mass loss rate of 3I Atlas was about 150 kilograms per second. Every second, the comet lost the weight of an adult human, sublimating, crumbling, leaving behind a trail of gas, dust, and metal vapors. Per day, this added up to almost 13,000 tons. In a month of approaching the sun, the comet would lose hundreds of thousands of tons of material it had kept frozen for millions of years. This was a slow death, a drawn-out agony of an interstellar wanderer that came too close to an alien sun. But the strangest surprise lay ahead. In mid-October 2025, the Keck 2 telescope in Hawaii detected something in 3I Atlas that shouldn't exist, an anti-tail. Normally, comet tails point away from the sun, blown out by solar wind and pushed by light pressure. But in some comets, under certain geometric conditions, an illusory tail appears pointing toward the sun, a projection effect where dust particles lagging behind the nucleus and left behind it in orbit appear from Earth as a glowing appendage ahead of the comet. 3I Atlas's anti-tail was clearly visible, as if the comet was extending a tentacle toward the sun, reaching for it with some strange persistence. For those looking for something unusual in the comet, this anti-tail became another argument. Why does an interstellar object develop such a rare feature? Why did the geometry of its orbit and dust distribution align exactly this way? Coincidence after coincidence? Anomaly after anomaly? Red color, excess carbon dioxide, nickel without iron, anti-tail, and all this crowned by the perfect alignment of trajectories with two Earth spacecraft. The calculated nucleus diameter was about 20 kilometers, a huge ice chunk carrying within itself memory of another star system. The comet was moving at 60 kilometers per second relative to the sun, or 210,000 kilometers per hour, a speed impossible to slow down, impossible to hold with our sun's gravity. After passing perihelion, it would turn around and return to interstellar darkness, taking with it secrets that scientists wouldn't have time to solve, unless the flyby through its tail gave answers to some questions. By mid-October, the scientific community split into two camps. Some claimed all 3I Atlas's anomalies were explained by natural processes, unusual chemical composition of the protoplanetary disk where it was born, prolonged exposure to cosmic radiation, random variations in nucleus structure. Others whispered about stranger possibilities. What if the red color isn't radiation damage but a coating applied deliberately? What if the anti-tail isn't an optical illusion but a sign of controlled movement? What if nickel carbonyl forms not by chance but is synthesized inside the object for some purpose? The Harvard astrophysicist, the same one who proposed the hypothesis about Oumuamua's artificial origin, made a new statement. He called on people to be ready for surprises and even vaguely hinted that October 29th could become a turning point in human history. His colleagues rolled their eyes, called it sensationalism, an attempt to attract attention. But online, on forums and social media, the scientists' words found fertile ground. People started following the comet, looking for signs in its behavior, building theories. And the comet continued approaching the sun, indifferent to human arguments. Its green coma expanded, reaching hundreds of thousands of kilometers in diameter. The ion tail stretched out like a glowing river, crossing planetary orbits. October 29th, 2025, the date of perihelion, stood circled in red on astronomers' calendars worldwide. On this day, the comet would be closest to the sun, its activity would reach maximum, and somewhere out there in the emptiness of space, two Earth spacecraft would be preparing to enter its tail and perhaps touch one of the greatest mysteries of the universe. On October 21, 2025, NASA added 3I Atlas to the Sentry list, a special database of potentially hazardous objects requiring constant monitoring. This decision triggered a wave of concern online, though astronomers rushed to calm the public. The minimum distance to Earth would be 270 million kilometers, almost twice the distance to the Sun. No collision threat existed, or could exist, but the very inclusion of an interstellar object in the hazardous celestial body monitoring system seemed symbolic, as if the agency was acknowledging, this visitor requires special attention. Calculations showed that the closest approach to Earth would occur on December 19, 2025. By that time, the comet would already turn around after perihelion and begin leaving the inner solar system. The distance of 1.8 astronomical units, about 270 million kilometers, was safe but close enough for detailed observations from Earth. November and December promised to be the time when the comet would emerge from solar glare and become accessible to amateur telescopes. Astronomy enthusiasts worldwide were preparing equipment, calculating ephemerides, planning photo sessions of the interstellar visitor. But they had to make it to December 1st. October 29th stood before the scientific community like an invisible wall. On this day, the comet would reach perihelion, finding itself 126 million kilometers from the Sun, roughly midway between the orbits of Earth and Mars. Its activity would peak. Solar radiation would vaporize ice with unprecedented intensity. During these days, give or take a few, somewhere in the emptiness of space, the trajectories of Europa Clipper and Hera might cross the ion tail. Might, but not necessarily. The uncertainty tormented scientists more than the lack of opportunity. At the Southwest Research Institute in San Antonio, Texas, a group of planetary scientists was working on an urgent proposal for NASA. They wanted to create a specialized mission for intercepting interstellar objects, a spacecraft that would be stored in readiness in Earth orbit and could launch at any moment when a new visitor from beyond the solar system is discovered. The idea wasn't new. Similar concepts had been discussed since Oumuamua's discovery. But now, with 3I Atlas proving that interstellar comets are not a one-time phenomenon but regular visitors, the project gained urgency. The problem was time. From the moment an interstellar object is detected to its departure from the inner solar system, only a few months pass. Preparing and launching a mission in such a time frame is impossible. Normally, from concept to launch takes years, sometimes decades. This means the probe must be ready in advance, waiting in orbit, and upon target discovery, receive commands, calculate an intercept trajectory, fire engines, and set off in pursuit. But who would finance building a spacecraft that might spend years waiting until chance gives it a target? 3I Atlas became an argument in favor of such a mission. 3 interstellar objects in 8 years, Oumuamua in 2017, Comet Borisov in 2019, now 3I Atlas in 2025. Statistics hinted that every few years, something from interstellar space passes through the inner solar system. Most such objects probably go unnoticed, too small, too dim, passing too far away. But those we do detect give us a chance to touch the mysteries of other star systems, to understand planet formation processes in different corners of the galaxy. Scientists from the National Optical Infrared Astronomy Research Laboratory published a statement emphasizing the importance of studying interstellar comets. These objects carry information about chemical elements present at the time and place of their formation. They provide insight into how planetary systems were created around distant stars throughout the galaxy's history, including systems around stars that long ago burned out and turned into white dwarfs or neutron stars. Each interstellar comet is a time capsule, a message from the past, from another place, from conditions that could have been completely unlike those in our solar nebula 4.5 billion years ago. The age of 3I Atlas was estimated at about 7 billion years. This meant the comet formed long before the birth of the Sun and Earth, in an era when the galaxy was younger, when second-generation stars were just beginning to enrich the interstellar medium with heavy elements synthesized in the cores of their predecessors. 7 billion years of wandering in cold and darkness, crossing light years of void, possibly passing dozens of star systems, but never lingering, never falling into gravitational captivity. Until now. Until meeting the Sun, the comet's activity at a distance of 2.9 astronomical units from the Sun, about 434 million kilometers, continued to puzzle researchers. At such a distance, solar radiation is too weak for water ice sublimation from the surface of most comets. However, observations showed that 3I Atlas was releasing water vapor at a rate of about 40 kilograms per second. For comparison, typical solar system comets at such distances are either completely inactive or release water in amounts an order of magnitude smaller. Calculations showed if water were evaporating only from the nucleus surface, the active area would have to be at least 7.8 square kilometers, more than 8% of the comet's entire surface. In ordinary solar system comets, only 3 to 5% of the surface is active, and that at much smaller distances from the Sun. The only explanation was that water was sublimating not just from the nucleus, but from the surrounding cloud, the coma. Numerous small ice grains in the coma absorbed sunlight more efficiently than the monolithic nucleus, heated up quickly, and ejected water vapor into space. This feature made 3I Atlas an ideal target for remote study. Abundant gas release created a dense coma, extended tails, strong spectral lines, everything that could be observed with telescopes and spectrometers. But the same feature meant the comet was rapidly losing mass, sublimating, crumbling, leaving behind a trail of material. 150 kilograms per second at peak activity, 13,000 tons per day. How long could the comet maintain such intensity? Weeks? Months? Or maybe the approach to the Sun would prove fatal, and the comet would break apart, fragment into pieces, as happened with other comets that came too close to the Sun. History knew many cases of comet breakup. In 1994, comet Shoemaker-Levy 9, torn apart by Jupiter's tidal forces, crashed into the giant planet's atmosphere as a chain of 21 fragments, leaving dark scars the size of Earth. In 2011, Comet Lovejoy passed through the solar corona and survived but lost a significant portion of its mass. In 2013, Comet Ison, called the Comet of the Century, approached too close to the Sun and almost completely vaporized, leaving only a dust cloud. What awaited 3I Atlas? Would it survive passing perihelion, or become another victim of solar heat? On October 23rd, with 6 days until perihelion, active discussion began on social media and specialized forums. Some users claimed they were observing strange changes in the comet's brightness, pulsations that didn't fit models of natural sublimation. Others reported unusual spectral lines that supposedly didn't correspond to any known chemical element. Professional astronomers called for caution, reminded about the need for careful data calibration, that Earth's atmosphere distorts observations, that amateur equipment doesn't always give reliable results. But scientists' skepticism didn't stop those who wanted to see something more in the comet than an ice chunk. A discussion thread appeared on Reddit with the headline, 3I Atlas, Natural Object or Something Else, which in a day gathered tens of thousands of views and thousands of comments. Users shared theories, from relatively restrained assumptions about unusual chemical composition to outright fantastic ideas about an alien probe masquerading as a comet. The Harvard astrophysicist, already having become a symbolic figure for enthusiasts of artificial interstellar object theories, gave several interviews where he cautiously, but persistently, spoke about the need to keep minds open to unexpected possibilities. His colleagues from other universities and research centers expressed irritation. Science requires evidence, they said, not speculations bordering on fantasy. All observed features of 3I Atlas, red color, excess carbon dioxide, strange behavior of nickel and iron, anti-tail, early activity, have natural explanations. Unusual, yes. Requiring further study, absolutely. But nothing points to artificial origin. Nothing requires invoking the hypothesis of alien intelligence. Occam's razor should work in astronomy too. Don't multiply entities unnecessarily. Choose the simplest explanation consistent with the data. And yet, coincidences kept accumulating. On October 24th, 5 days before perihelion, it became known that the Europa Clipper mission team decided to turn on the magnetometer and PIMS particle detector in enhanced sensitivity mode precisely during the period from October 30th to November 6th. The official wording was vague. Additional scientific observations as feasible, not affecting the mission's primary objectives. But those following the developments understood, NASA decided to try. Information from the arc of paper reached the right people, calculations were verified, risks assessed, and the decision made. Europa Clipper would search the emptiness of space for the trail of an interstellar comet. There was no news from Hera. The European Space Agency remained silent, and it was unclear whether the mission team was planning any special observations. Perhaps the lack of suitable instruments made any attempts pointless. Perhaps engineers were too busy with primary tasks, navigation to the Didymos asteroid system, checking spacecraft systems, preparing for future work. Space missions are always a balance between ambitions and limitations, between the desire to explore everything and the need to focus on primary goals. On October 25th, the first day of the time window for Hera's possible trajectory crossing with the Ion tail, dozens of amateur astronomers worldwide pointed their telescopes at the area of sky where the comet should be. It was already too close to the sun for comfortable observations. Eastern sky at dawn, low above the horizon, in the rays of morning twilight. But some managed to capture faint greenish glow blurred by atmospheric haze. 3I Atlas continued its journey to perihelion, indifferent to human hopes and fears, to scientists' debates and enthusiasts' dreams. At NASA's Jet Propulsion Laboratory in Pasadena, engineers and scientists of the Europa Clipper team were preparing for an unusual task. The spacecraft was several astronomical units from Earth, continuing to accelerate, using the gravity of inner planets to gain the speed needed to reach the Jupiter system. Its trajectory was calculated with incredible precision, every maneuver planned, every joule of energy accounted for. And now, in the middle of this strictly calibrated flight, the spacecraft had to try to detect something ephemeral, rarefied comet tail plasma passing somewhere out there in the emptiness of space, millions of kilometers from the central axis. The team uploaded a special observation program to the onboard computer. PIMS would begin continuous registration of charged particles starting October 30th. The magnetometer would measure the magnetic field at maximum sampling rate. Data would be recorded in onboard memory. Then, when the spacecraft establishes contact with Earth, transmitted to the Jet Propulsion Laboratory for analysis. No one knew what exactly would be discovered. Maybe nothing. Solar wind, ordinary plasma, no signs of cometary material, maybe a weak signal, barely noticeable change in composition, a hint of water or carbon dioxide ions. Or maybe, if lucky, if geometry aligned right, if solar wind didn't blow the tail sideways, a clear, unambiguous peak in cometary ion concentration, the chemical signature of interstellar matter. On October 27th, 2 days before perihelion, 3I Atlas entered an area inaccessible to observations from Earth, too close to the sun, too bright a background, impossible to make out the faint glow of the coma in our star's radiance. For several weeks, the comet would disappear from the field of view of Earth telescopes, hide in solar rays, and only space observatories, like SOHO or Parker Solar Probe, if their trajectories proved suitable, could attempt to record its perihelion passage. It was like an actor going backstage before the final act. What would happen there, in close proximity to the sun, in the cauldron of solar radiation and solar wind? Would the comet endure or crumble into fragments? On the evening of October 28th, an amateur astronomer from Argentina published on Twitter the last photograph of 3I Atlas before its disappearance into sunlight. The image was grainy, blurred by atmospheric turbulence, but the green coma was clearly visible, with a faint, barely distinguishable tail stretching behind it. The post got tens of thousands of likes and was quoted by hundreds of users. "Farewell, wanderer," someone wrote in the comments. "See you in December," another replied. "If it survives tomorrow," a third added. And this uncertainty, this not knowing what would happen in the coming hours, made the moment especially dramatic. Humanity, armed with telescopes and spacecraft, still remained in ignorance before cosmic events unfolding, according to the laws of physics, indifferent to our observations. On October 22nd, 2025, while most of humanity was going about their daily business, an event occurred on the far side of the sun that could change the fate of the interstellar wanderer. A powerful coronal mass ejection burst from the solar atmosphere, hurling billions of tons of superheated plasma into space. Such events happen regularly. The sun lives in an 11-year activity cycle, and during peak periods, ejections occur several times a week. But this one was special. The Solar Astronomy Laboratory of the Space Research Institute of the Russian Academy of Sciences calculated the plasma cloud's trajectory and discovered something astonishing. The ejection was headed precisely, with an error of only 10 to 20 degrees, toward where 3I Atlas should be. The plasma cloud was moving at about 800 kilometers per second, almost 3 times faster than normal solar wind. Temperature inside the cloud reached millions of degrees. The magnetic field frozen into the plasma was distorted, twisted, ready to compress and deform any magnetosphere in its path. Astronomers quickly calculated the ejection front would reach the comet around 3 p.m. Moscow time on October 24th, Friday, and the comet would be inside the plasma cloud for at least a day and a half to 2 days, immersed in a storm of charged particles, magnetic fields, energy capable of ripping off the tail, destroying the coma, possibly even splitting the nucleus itself if it proved insufficiently robust. Scientists from the Solar Astronomy Laboratory couldn't resist a joke. "Well, let's see how the aliens handle weather sensitivity," they wrote in their message, alluding to H.G. Wells' War of the Worlds, where highly advanced Martians died from Earth microbes. The joke was nervous. You could feel the tension behind it. Because no one knew what would happen when superheated plasma struck an ancient comet that had traveled billions of years in the cold of interstellar space. Would it endure? Would its activity change? Or would the solar explosion be a death blow to the wanderer who had come so far? On October 23rd, a day before the predicted collision with the plasma front, several observatories tried to point telescopes at the area where the comet should be. The task was nearly impossible. 3I Atlas was on the opposite side from the sun, immersed in the bright glow of the corona, inaccessible to optical observations from Earth. The SOHO and Stereo Space Solar Observatories could potentially detect the comet if their coronagraphs happened to be pointed at the right area, but data from these spacecraft arrived with delays, processed slowly, and following events in real time was impossible. The comet found itself in humanity's blind spot precisely at the moment when something dramatic was supposed to happen to it. Friday, October 24th, 3 p.m. Moscow time. In these minutes, somewhere about 200 million kilometers from the Sun, with a slight shift toward the northwest, the coronal plasma front reached 3I Atlas. The shock wave passed through the rarefied coma, compressing it, deforming it, sweeping away ions and molecules that had just evaporated from the nucleus surface. The magnetic field carried by the plasma flowed around the comet, creating a turbulent wake behind it. Solar wind pressure, normally a few nanopascals, suddenly increased by tens, maybe hundreds of times. It was like a hurricane descending on a lone tree in the steppe. The comet stood in the emptiness of space, defenseless before the fury of a nearby star. On Earth, no one saw what was happening. Astronomers built models, ran simulations, tried to predict effects. Theoretically, the coronal plasma impact could temporarily strip the comet's ion tail, carry it away, dissolve it in the stream of charged particles. Theoretically, it could increase sublimation activity, heat the surface, trigger sudden releases of gas and dust. Theoretically, it could split the nucleus if there were cracks inside the comet, weak spots, areas with elevated pressure of volatile substances. History knew cases when comets disintegrated without apparent cause, simply broke into fragments, as happened with Comet Schwarzmann-Wachmann 3 in 1995. But never before had anyone observed a coronal ejection hitting an interstellar comet at the critical moment of its approach to the Sun. The comet was supposed to spend a day and a half to 2 days inside the plasma cloud. This meant that all of the 24th, 25th, and part of the 26th of October, 3I Atlas would be immersed in anomalous conditions, elevated density of charged particles, strong magnetic fields, solar wind turbulence. It was during this time that Hera was entering its time window for possible tail crossing from October 25th to November 1st. But if the tail was stripped by the plasma impact, if the comet temporarily lost its gas envelope, then the crossing might yield no results. The European spacecraft would fly through emptiness where interstellar matter ions should have been, and detect nothing. On October 25th, Saturday, while solar plasma still enveloped the comet, amateur astronomers on forums discussed the latest news. Someone claimed to have seen a flash in the SOHO coronagraph, possibly related to the comet. Someone suggested the plasma impact wasn't a coincidence, but a deliberate action, as if the Sun was defending itself against an outsider, attacking a visitor from another star system. Of course, these were fantasies, projections of human emotions onto indifferent physical processes. The Sun has no mind, cannot attack or defend itself. Coronal ejections result from magnetic reconnection in the star's atmosphere, a natural phenomenon obeying plasma physics laws. But the coincidence seemed too perfect. An interstellar comet and a solar blast precisely in the direction of its trajectory. On October 27th, the plasma cloud moved on, leaving the comet behind. Conditions returned to normal solar wind. And here, something amazing happened. Observations from the Nordic Optical Telescope, published that same day, showed that 3I Atlas's tail had sharply changed direction. Previously, it had been pointed toward the Sun, the mysterious anti-tail that had puzzled astronomers. Now the tail faced away from the Sun, as a normal comet should. As if the plasma impact had reset the system, returned the comet to its natural state. Scientists explained this change as follows. Initially, large dust particles slowly moving along the comet's orbit and lagging behind the nucleus reflected light toward the sun, creating the anti-tail illusion. But when the comet approached close enough that temperature rose sharply, intense water ice sublimation began. Carbon dioxide, which had dominated at greater distances, gave way to water vapor. This process triggered formation of a normal ion tail, directed away from the sun by solar wind. Particles in the tail reacted differently to radiation pressure and magnetic field. Heavy ones moved slower, light ones faster, creating a complex dynamic structure. The change in composition of emitted material, from carbon dioxide to water, confirmed data obtained by the James Webb Space Telescope and Swift Telescope a month earlier. At large distances, carbon dioxide dominated. At close ones, water. The comet demonstrated a layered structure. Outer layers rich in frozen carbon dioxide sublimated first. Inner layers consisting predominantly of water ice were exposed as it approached the sun. This was a clue about the comet's formation process in that distant protoplanetary system. It grew in layers like an onion, capturing material from different disk regions where temperature and composition differed. On October 28th, a day before perihelion, the European probe JUICE team, Jupiter Icy Moons Explorer, announced readiness to conduct observations of 3I Atlas. This spacecraft, launched in April 2023 and heading to Jupiter's icy moons, found itself in a relatively favorable position to observe the comet after its perihelion passage. Observations were scheduled from November 2nd to 25th, nearly a month of continuous monitoring. JUICE uses 5 scientific instruments, including cameras, an infrared imager, an ultraviolet spectrometer. The distance from the probe to the comet would be enormous, but the instruments are sensitive enough to record brightness, color, spectral features. There was one catch: data wouldn't arrive immediately. JUICE's position relative to Earth was such that information transfer speed was extremely low. ESA project scientist Olivier Witasse warned, data is expected to be downloaded only in February 2026. 3 months of waiting, 3 months of uncertainty. The comet would be observed, measured, photographed in November, but humanity would learn the results only in winter of next year. It was like taking a photograph, but only being able to develop the film in a quarter. October 29th, 2025. Perihelion Day. Comet 3I Atlas reached the closest point of its trajectory to the Sun, 126 million kilometers, 0.8 astronomical units, roughly where Earth's continents once formed, where oceans gathered water from billions of collisions with comets and asteroids, where life originated at this distance from the Sun. The alien wanderer passed its critical point. Solar radiation was vaporizing ice at maximum intensity. Temperature on the illuminated side of the nucleus could reach 200 to 300 degrees Celsius. The unlit side remained at -150, -200. Cosmic cold barely softened by reflected heat from the coma. The comet survived. It didn't split, didn't vaporize. Continued moving, leaving behind a multi-million kilometer tail of ionized gas and dust. Somewhere out there in the emptiness of space, several astronomical units away, 2 Earth spacecraft awaited their moment. Hera had already entered the time window. The 25th of October had passed. The 26th, 27th, 28th. Each day was a potential crossing point with the ion tail. Each hour instruments recorded data, either silence or weak solar wind background, or maybe barely noticeable changes that later, with detailed analysis, would prove to be traces of interstellar matter. Europa Clipper was preparing to enter its window. From October 30th to November 6th, the magnetometer and PIMS particle detector were switched to enhanced sensitivity mode. Onboard memory was cleared, ready to receive new data. Jet Propulsion Laboratory engineers checked and rechecked the software. Everything was ready. All that remained was to wait and hope that geometry would align correctly, that the tail catcher model would prove accurate, that solar wind wouldn't blow the tail sideways, that 8 million kilometers from the central axis wouldn't prove too far to detect a signal. On October 30th, a day after perihelion, when the comet began moving away from the Sun but still remained invisible from Earth due to proximity to the Sun, Europa Clipper entered the zone of possible crossing. The spacecraft flew through emptiness at tens of kilometers per second, heading toward distant Jupiter. Instruments worked, recording the flow of charged particles, protons and electrons of solar wind, alpha particles, rare heavy ions. Data was saved to memory, awaiting the moment when the antenna would turn toward Earth and information transmission would begin across the boundless expanses of space. Scientists on Earth knew nothing. They could only calculate, model, hope. Did Europa Clipper pass through the tail? Did its instruments detect anything unusual? Or did the spacecraft fly past, a few million kilometers from the invisible plasma tube, and the opportunity was missed? Answers would come later, in days, in weeks, when data arrived on Earth, would be processed, analyzed, compared with models. For now, there was only waiting, and this waiting was almost unbearable for those who had devoted months to planning this improvised encounter with an interstellar guest. On November 1st, 2025, when Comet 3I's Atlas had already passed perihelion and begun moving away from the Sun, the moment of truth arrived at NASA's Jet Propulsion Laboratory in Pasadena. Europa Clipper had completed its passage through the calculated ion tail zone. From October 30th to November 1st, the spacecraft moved through a region of space where, according to the tailcatcher model, rarefied plasma of cometary material should have been. Instruments worked continuously. The magnetometer recorded magnetic field fluctuations several times per second. The PIMS particle detector registered every ion, every electron entering its Faraday cups. Terabytes of data were recorded in onboard memory, awaiting transmission to Earth. But data transmission from a distance of several astronomical units is a slow and meticulous process. Europa Clipper's antenna had to aim precisely at Earth, accounting for the spacecraft's velocity, the planet's rotation, the movement of both targets along their orbits. Transmission speed was several kilobits per second, thousands of times slower than home internet. Priority went to data about the spacecraft's condition, system temperatures, tank pressure, battery charge, spatial orientation. Scientific information stood in queue. Engineers estimated that first data from the magnetometer and PIMS would start arriving no earlier than November 3rd, 4th, with the full observation set downloaded by the end of the month's first week. Scientists waited. In Jet Propulsion Laboratory offices, in university cabinets around the world, on amateur astronomers' home computers, everywhere people refreshed pages, checked email, followed publications in preprint archives. Did Europa Clipper detect anything at all? Did the spacecraft pass close enough to the tail's axis? Or did 8 million kilometers prove too great a distance, with plasma so rarefied it dissolved into the background of ordinary solar wind? This question tormented those who had spent months preparing observations, calculating trajectories, convincing mission leadership to allocate resources for additional measurements. Hera completed its time window on November 1st. The European spacecraft passed through the calculated region from October 25th, 5 days of possible tail crossing. But without a magnetometer, without a particle detector, chances of detecting anything were negligible. Cameras captured only the emptiness of space, black background studded with distant stars, A rarefied comet's ion tail is invisible at close range. It doesn't reflect light, doesn't cast shadows. You can pass right through it and not notice without special instruments. The Hera mission team returned to their primary tasks, preparing for the encounter with the Didymos asteroid system, scheduled for October 2026, a year after these events. On November 3rd, first data fragments from Europa Clipper began arriving. A team of plasma physics specialists gathered before monitors, viewing graphs of ion concentration, particle energy spectra, magnetic field vectors. The first hours showed nothing unusual. Standard solar wind, protons and alpha particles, calm magnetic field of interplanetary medium. But then, in data from October 31st, around 14:01 UTC, an anomaly appeared. Small, barely noticeable, but statistically significant. Oxygen ion concentration increased about 15 to 20% above background level. Simultaneously, traces of carbon and hydrogen ions appeared in unusual proportions. Specialists leaned closer to screens. Oxygen ions are always present in solar wind, but in small quantities, about 1% of protons. Here, concentration temporarily rose to 1.5%, maybe slightly more. To the uninitiated, this sounded like a negligible change, like noise, like statistical fluctuation. But physicists knew, in cosmic plasma, any deviations from normal have a cause. Solar wind is remarkably constant in composition over large timescales. If some element's concentration suddenly changes, it means something else mixed into the solar wind. Another ion source, another origin of matter. The magnetometer showed weak disturbance. Field lines of interplanetary medium's magnetic field slightly curved, as if flowing around an obstacle. The effect was barely distinguishable against ordinary turbulence, but its direction coincided with the expected comet tail geometry. If we assume 3I Atlas's tail indeed crossed Europa Clipper's trajectory at this moment, the magnetic field should have behaved exactly this way, curving, draping around the cometary plasma flow, creating the characteristic structure known as a magnetic tail behind an obstacle. The data hinted at something's presence, but didn't shout about it. On November 4th, data continued arriving, and the picture became clearer. The ion concentration anomaly lasted about 3 hours, from 14 Sound to 17 AU UTC on October 31st. Then everything returned to normal. 3 hours. During this time, Europa Clipper, moving at about 40 kilometers per second, covered more than 400,000 kilometers. Typical ion tail width at 8 million kilometers from the central axis could be several 100,000 kilometers. The numbers matched. The temporal profile, concentration rise, plateau, decline, corresponded to passing through a finite-sized structure. But skeptics on the team pointed to alternative explanations. Maybe this was a local ejection from the solar corona, unrelated to the comet. Maybe a magnetic structure in the solar wind coincidentally compressed and heated a small plasma volume, changing the ion ratio. Maybe instruments gave a false trigger, a data artifact that would disappear upon recalibration. Careful analysis was required. Comparison with other flight periods, checking for correlation between different instruments, searching archives of data from other missions that passed through comet tails. This was work not for days, but weeks, maybe months. On November 5th, when most of the full data set was downloaded to Earth, the Europa Clipper mission team held an internal meeting. Discussion was closed, without press releases, without public statements. The project's scientific director formulated the position cautiously. Yes, we see potential signs of interaction with cometary material, but additional analysis is required for confirmation. No, we cannot definitively state that Europa Clipper flew through 3I Atlas's tail. Yes, results are encouraging, but science demands rigor and patience. Publication of results is scheduled for December after completing all checks. This caution disappointed those craving immediate sensations. On social media and forums, speculation began. What exactly is NASA hiding? Why not publish data immediately? Maybe something so unusual was discovered that time is needed to prepare the public. Or conversely, nothing was found, and now they're trying to justify spent resources? Conspiracy theories bloomed luxuriantly. Especially active were those who believed in 3I Atlas's artificial origin. They claimed the spacecraft detected signs of technological activity, radio signals, modulated radiation, structured magnetic fields, and NASA was now deciding how to present this to the world. On November 8th, the JUICE scientific group, the European probe to Jupiter's moons, announced it had begun a series of 3I Atlas observations. The spacecraft was at such a distance and angle that it could see the comet after its perihelion passage, when it began moving away from the sun, but still remained bright enough for detection. High-resolution cameras, ultraviolet spectrometer, infrared imager, all instruments were engaged to obtain maximum information. But as warned back in late October, data would arrive on Earth only in February 2026. Low transmission speed and antenna occupation with primary mission tasks meant a long wait. Meanwhile, the comet continued its journey. On November 9th, it was about 200 million kilometers from the sun, moving away at 25 kilometers per second. Sublimation activity declined. Solar radiation weakened each day. Surface temperature of the nucleus dropped. Gas emissions became less intense. But the comet still displayed a tail, still glowed green from diatomic carbon decay. Calculations showed that by late November, it would emerge from the blind zone caused by proximity to the sun and again become accessible for observations from Earth. Astronomy enthusiasts worldwide prepared telescopes, planned photography sessions, exchanged coordinates and ephemerides. On November 15th, an event occurred that poured oil on the fires of speculation. A small group of astronomers from Argentina, observing 3I Atlas with a meter telescope at El Leoncito Observatory, published on Twitter a series of comet images taken from the 10th to 14th of November. In these images, after processing and contrast enhancement, strange structures were visible in the coma. Several bright points arranged almost symmetrically around the nucleus, and something resembling a spiral pattern in the dust tail. The image authors cautiously called this unusual features requiring further study. The internet exploded. Symmetrical bright points? Spiral pattern? For some, these were signs of jet emissions from localized active regions on the rotating nucleus, a completely natural phenomenon observed in many comets. Nucleus rotation creates a pinwheel effect. Gas flies out from specific points, and if the nucleus spins, these emissions trace spiral trajectories in space. For others, these were antennas, engines, technological elements of an alien probe that could no longer hide its true nature. Debates and comments became increasingly heated, moving from scientific argumentation to personal attacks. The professional astronomy community called for calm. An International Astronomical Union representative issued a statement. All observed features of 3I Atlas fit within the framework of natural processes known for comets. The object's unusualness stems from its interstellar origin, which implies different chemical composition, different formation history, different conditions in which it existed for billions of years. But nothing points to artificial origin. Nothing requires invoking the hypothesis of extraterrestrial intelligence. The call for scientific rigor and restraint sounded in numerous articles, interviews, publications in popular science outlets. On November 19th, when the comet became visible to powerful amateur telescopes from the southern hemisphere, Dozens of observers captured it simultaneously. Images flooded social media, forums, specialized websites. Green coma blurred by atmospheric haze, faint tail stretching several arc minutes. The comet was dimmer than expected, apparent magnitude about 10, accessible only to telescopes with aperture from 20 centimeters. But for those who had followed its fate since the July 1st discovery, the comet's very appearance in view was an event. It survived, passed perihelion, withstood the coronal plasma impact, continued its path away from the inner solar system toward where it came from, interstellar abyss. On November 23rd, a research group from the Finnish Meteorological Institute, the same ones who calculated Europa Clipper and Hera's tail-crossing trajectories and published the Arxiv paper, issued an update to their calculations. Considering new solar wind data obtained from Parker's Solar Probe and Solar Orbiter, plus information about the October 22nd coronal ejection, they revised the tail geometry model. It turned out the plasma impact indeed shifted the ion tail several million kilometers sideways, but not for long. By October 31st, the tail recovered roughly in the expected configuration. The probability that Europa Clipper passed through the tail's periphery was now estimated at 60 to 70%, higher than the initial 50%, but still not absolute certainty. These numbers gave hope. If probability is 60 to 70%, then anomalies in magnetometer and PIMS data recorded on October 31st most likely really are related to cometary material. But final confirmation required comprehensive analysis, comparing isotopic composition of detected ions with data obtained by James Webb Telescope and other instruments, modeling plasma propagation from nucleus to crossing point, excluding all alternative explanations. This work continued in laboratories and universities, slowly, carefully, checking every assumption. By late November, 3I Atlas was about 300 million kilometers from the Sun, 2 astronomical units, roughly where the outer edge of the asteroid belt lies. Activity was falling, the tail dimming, but the comet was still alive, still observable. Ahead lay December 19th, the day of maximum approach to Earth at a distance of 270 million kilometers. This would be the last convenient moment for detailed observations before the comet went too far and became inaccessible even to the largest telescopes. Astronomers planned to use this chance to the maximum. Spectroscopy, photometry, polarimetry, everything that could be squeezed from the ancient wanderer before its return to interstellar darkness. On December 1st, 2025, Comet 3I Atlas was 350 million kilometers from the Sun, slowly receding into the outer solar system. Sublimation activity had dropped to several tens of kilograms per second, 5 times less than the late October peak. The green coma shrank, grew dimmer, but still enveloped the nucleus in the ghostly glow of diatomic carbon. The ion tail, once stretched millions of kilometers, now barely reached a few 100,000, faintly glowing in the ultraviolet range. The comet was dying a slow death, not disintegrating, not splitting, simply freezing back, returning to the state of icy silence in which it had spent billions of years of interstellar travel. Southern Hemisphere astronomers gained the observational advantage. From Chile, Argentina, Australia, South Africa, dozens of observatories, professional and amateur, pointed telescopes at the dimming wanderer. Magnitude fluctuated between 11 and 12 at the threshold of visibility for average amateur equipment. Dark skies away from city lights were needed. A telescope with mirror diameter of at least 20 centimeters, patience and experience. Long exposure photographs revealed a faint oval coma, sometimes a hint of tail, barely distinguishable stretching of glow in one direction. To the naked eye, even through a powerful telescope's eyepiece, The comet looked like a hazy speck, indistinguishable from distant galaxies, if not for its slow drift against the stars. On December 5th, a group of astronomers from Cerro Tololo Observatory in Chile published a series of 3I Atlas spectra obtained over the previous week. Spectra showed emission lines of cyanogen, diatomic carbon, water ions, standard fare for a comet. But the ratios were unusual. There was less cyanogen than expected for a comet of this size and activity. Diatomic carbon, conversely, more. This hinted at a nitrogen deficit in the comet's composition, an element necessary for cyanogen formation. Where did such an anomaly come from? Maybe the protoplanetary disk where the comet was born was nitrogen poor, or nitrogen sublimated earlier, at greater distance from the sun, before detailed spectral observations began. On December 10th, an amateur astronomer from Namibia, observing the comet through a 30-centimeter reflector, noticed something strange. In two sequential images taken 2 hours apart, the coma's brightness changed by about 15%. The change was localized. Not the entire coma brightened, but only an area on one side of the nucleus. The astronomer published the images on a forum, asking colleagues' opinions. Different explanations were offered. Perhaps a sudden gas and dust release from an active region on the nucleus, a so-called jet or outburst. Such events happen when solar heat penetrates subsurface layers, vaporizes ice, pressure builds, and a micro-explosion occurs, ejecting material into space. But others pointed out, the comet is already far from the sun. Temperature is low. Where's the energy for such an ejection? Maybe the nucleus rotates, and the observer simply saw a brighter side that was previously turned in another direction? Or was it an effect of Earth's atmosphere? Turbulence, clouds, changing sky transparency. Without confirmation from other observatories, there was no way to say for sure. But for those looking for signs of unusual behavior in the comet, this episode became another puzzle piece. Local brightness changes, as if something inside the object was working. Something was controlled. Something was reacting. On December 14th, the comet was about 280 million kilometers from Earth, roughly 1.9 astronomical units. 5 days remained until maximum approach on December 19th. Major observatories planned to use this window for final detailed observations. The Very Large Telescope in Chile allocated 3 nights, December 16th, 17th, and 18th, for spectral and photometric measurements. The Hubble Space Telescope requested time for ultraviolet spectroscopy, studying ion emission lines invisible from Earth's surface due to atmospheric absorption. The James Webb Space Telescope planned another infrared observation session to check how the coma's chemical composition had changed compared to August data. On December 16th, when the Very Large Telescope turned its 8-meter mirrors toward 3I Atlas, astronomers discovered something unexpected. Weak lines appeared in the spectrum that hadn't been there before: methanol and formaldehyde emission. These organic molecules are sometimes detected in comets, but usually at much smaller distances from the sun, when temperature is high enough for their sublimation. Yet here, the comet was more than 3 astronomical units from the sun, in a region where temperatures shouldn't exceed -150 degrees Celsius. Where did the methanol and formaldehyde come from? Maybe they were sublimating not from the nucleus surface but from fine dust particles in the coma, heated by sunlight more strongly than the monolithic nucleus. Or, some suggested, chemical reactions releasing heat were occurring inside the nucleus. Radioactive decay of long-lived isotopes, exothermic reactions between minerals and organics, crystallization of amorphous ice, processes that could provide a weak but constant energy source sufficient for volatile organic molecule sublimation, even far from the sun. If so, then the comet isn't just a chunk of dead ice and rock, but an active chemical system where processes that began billions of years ago in a distant protoplanetary nebula continue. On December 17th, 2 days before maximum approach, the Juno space mission team, NASA's probe studying Jupiter, announced readiness to conduct 3I Atlas observations in March 2026. By that time, Juno would be at such a point in its orbit around Jupiter that it could aim instruments at the comet, already receded beyond Mars's orbit. Observations wouldn't be detailed, distance too great, but even crude brightness and color measurements would add information to the data pool, help build the complete light curve of the comet from its July discovery to final disappearance somewhere in mid-2026. On December 18th, the Hubble Space Telescope completed a series of ultraviolet observations. Preliminary data leaked to the scientific community through informal channels indicated strong emission lines of oxygen and carbon ions in the extreme ultraviolet, the spectral region where atoms emit after losing several electrons under harsh ultraviolet from the sun. The intensity of these lines was higher than other comets at comparable distances from the sun. This could mean 3I Atlas's coma contained more oxygen and carbon in gas phase, confirmation of high carbon dioxide content data obtained by James Webb Telescope in August. On December 19, 2025, Thursday, Comet 3I Atlas reached the closest point of its trajectory to Earth, 270 million kilometers, 1.8 astronomical units, almost twice as far as the distance from Earth to the Sun. A safe, enormous distance, but in cosmic scale, relatively close. This was the last convenient moment for observations before the comet went too far and became inaccessible even to the planet's largest telescopes. That night, thousands of people worldwide tried to see the interstellar wanderer with their own eyes through telescope eyepieces on camera screens attached to tubes. Most were disappointed. The comet was too dim, 12th magnitude barely accessible under ideal conditions, light pollution from cities, atmospheric haze, observer inexperience. All this made the task nearly impossible. But some got lucky. An amateur astronomer from Australia, observing from a remote station in the desert, captured a faint, hazy speck slowly crawling between stars in the constellation Eridanus. A photographer from Chile obtained a series of long exposure images where the coma looked like a ghostly oval surrounded by a scattering of distant galaxies. Social media filled with images, real and fake. Some passed off photos of other comets as 3I Atlas, craving likes and shares. Others published images of nebulae, galaxies, even simple camera sensor defects, claiming it was the interstellar guest. Professional astronomers tried to combat misinformation, published ephemerides, precise comet coordinates in the sky for each day and hour, so people could verify image authenticity. But stopping the wave was impossible. The comet became a meme, a symbol, an object of projection of human hopes and fears. On December 20th, the day after maximum approach, 3I Atlas began slowly moving away from Earth. Each day the distance increased by several million kilometers. Each night the comet became slightly dimmer, slightly smaller, slightly farther. By late December, its apparent magnitude dropped to 13th, beyond the reach of most amateur telescopes. Only major observatories could still detect the faint glow, and even then with difficulty, at the limit of detector sensitivity. On December 25th, Christmas, a small group of scientists and enthusiasts held an online conference dedicated to 3I Atlas observation results. Astronomers, planetary scientists, comet chemistry specialists spoke. They summarized preliminary results, without final conclusions, because data analysis continued. Red color indicating cosmic ray irradiation over millions of years. Excess carbon dioxide hinting at formation in a specific protoplanetary disk region. anomalous nickel-to-iron ratio, possibly related to exotic chemical processes. Early water release at great distances from the Sun, explained by sublimation from fine coma particles. Anti-tail that disappeared after the coronal plasma impact. Local brightness changes possibly related to nucleus rotation or sudden ejections. All these features, speakers emphasized, have natural explanations. Unusual, yes. Requiring further study, absolutely. But nothing goes beyond known physics and chemistry. Nothing requires invoking hypotheses about intelligent intervention. 3I Atlas is an interstellar comet, an ancient fragment of a distant planetary system that gave scientists a unique chance to study material formed under conditions different from solar ones. This is a treasure trove of data that will be analyzed for years. Papers will be published, dissertations defended, models built. Science received a gift, and that's enough. But those who wanted to believe in mystery remained unsatisfied. Too many coincidences, they said. Too many anomalies. Red color, like Oumuamua. Perfect trajectory alignment with Earth spacecraft. Coronal ejection that struck precisely at the comet. Symmetrical bright points in the coma. Local brightness changes, each detail separately explainable, but all together form a pattern that seems too complex for chance. Maybe, conspiracy theory enthusiasts said, truth is hidden in data not yet published. Maybe Europa Clipper detected something NASA is silent about. Maybe JUICE will see in November observations what will change everything. And that's exactly why data is delayed until February, to give governments time to prepare for disclosure. On December 31st, 2025, the last day of the year, Comet 3I Atlas was about 500 million kilometers from the Sun, more than 3 astronomical units, roughly where the middle of the asteroid belt lies. Apparent magnitude dropped to 14th. Sublimation activity almost ceased. Surface temperature of the nucleus dropped so low that even carbon dioxide could no longer sublimate in significant quantities. The coma shrank to a few thousand kilometers in diameter. The tail disappeared. The comet was transforming back into a silent ice chunk, as it was before meeting the Sun. That night, when humanity celebrated the new year, when cities blazed with fireworks, when people embraced and wished each other happiness, somewhere out there in the cold darkness between Mars and Jupiter's orbits, the ancient wanderer continued its path. 7 billion years it had traveled through the galaxy. Several months it spent in the embrace of an alien sun, and now it was returning to the interstellar abyss, carrying with it mysteries that people barely managed to touch. In a year, in 2, the comet will cross Jupiter's orbit, then Saturn's, Uranus's, Neptune's. In decades it will leave the Oort cloud, the outer boundary of the Sun's gravitational influence, and again will be free. Again will belong to the galaxy, not a star. Maybe in millions of years, it will visit another star system, other planets, other oceans and mountains not yet born. Maybe someday, in the distant future, another civilization will discover it and ask the same questions that tormented people in 2025. On January 14th, 2026, 2 weeks after the New Year holidays, when the world returned to its usual work rhythm, the Europa Clipper mission team published preliminary results analyzing data obtained during passage through the presumed ion tail region of 3I Atlas. The paper appeared in the Harcourt preprint archive late evening North American time, and by morning, thousands of researchers worldwide had downloaded it. The title was cautious, almost modest. Possible signs of interaction with cometary plasma, Europa Clipper observations in October-November 2025. But behind this restraint hid something important. The authors confirmed. On October 31st, during the period from 14 to 17 on UTC. The PIMS particle detector recorded a statistically significant increase in oxygen, carbon, and nitrogen ion concentration. The increase ranged from 15 to 30% above background level, depending on the element. The magnetometer during the same period registered magnetic field disturbance characteristic of the draping effect, when field lines flow around an obstacle in the form of a plasma stream. Ion energy spectra showed distribution different from typical solar wind, more low-energy particles, consistent with cometary origin. But the most interesting lay in isotopic analysis. The ratio of carbon-12 to carbon-13 in detected ions differed from solar by 2 to 3%. A small deviation, on the edge of statistical error, but stubbornly repeating in all measurements of that 3-hour interval. This hinted that carbon didn't come from the sun's atmosphere, but from another source, from matter formed under different conditions, at different temperature, in different chemical environment. From a protoplanetary disk around a distant star where Comet 3I Atlas was born billions of years ago. The authors emphasized uncertainty. We cannot assert with 100% confidence, they wrote, that the detected signal comes specifically from the comet. Alternative explanations exist. Local inhomogeneity in solar wind, residual effects from coronal ejections, instrumental artifacts. Confirmation from other data sources is required, comparison with observations from other missions, additional modeling. But the probability that Europa Clipper indeed passed through the periphery of 3I Atlas's ion tail and tasted interstellar matter was now estimated at 70 to 80%. High enough to speak of preliminary success, the scientific community reacted with restrained optimism. Comments in professional publications sounded cautious. Encouraging results, intriguing data, require further study. No one shouted about a breakthrough. No one declared victory. Science moves slowly, carefully checking every step. But behind the scenes, in emails between colleagues, in conversations over lunch at conferences, there was excitement. For the first time in history, a spacecraft heading to a completely different target accidentally crossed an interstellar comet's tail and detected signs of its material. A free bonus gifted by orbital geometry and luck. On January 21st, the research team from the Finnish Meteorological Institute, the same ones who first calculated the crossing possibility, published a detailed analysis of the event's geometry. They used updated solar wind models, data from Parker Solar Probe and Solar Orbiter, information about the October 22nd coronal ejection. Calculations showed that 3I Atlas's ion tail at the moment of Europa Clipper's passage extended about 20 million kilometers from the comet's nucleus. The spacecraft passed roughly 8 to 9 million kilometers from the central axis. Far, but not so far that the signal completely dissolved in background. At this distance, cometary ion concentration should have been 1 to 2% of total plasma density. Exactly what PIMS detected. On January 30th, a small group of astrophysicists from Leiden University in the Netherlands published a controversial paper. They claimed that anomalies in 3I Atlas's behavior, non-standard accelerations, brightness changes, strange metal ratios, cannot be fully explained by natural processes. By their calculations, releasing the observed amount of nickel at low temperatures required an additional heat source inside the nucleus. Radioactive decay of long-lived isotopes provided insufficient energy. Exothermic chemical reactions too. The question remained, where's the heat? Maybe, the authors suggested, inside the comet was something generating energy. An artificial source? A reactor? A battery working for millions of years? The paper triggered a wave of criticism, Colleagues accused the authors of insufficiently rigorous accounting for uncertainties, arbitrary selection of model parameters, desire to obtain a sensational result at any cost. The journal editor where the paper was submitted for review rejected it with the wording, "requires significant revision and additional justification of conclusions." But online, the paper got a second life. Enthusiasts of theories about 3I Atlas's alien origin cited it as proof. See, even scientists from a prestigious university cannot explain everything by natural causes, so the artificial hypothesis remains. On February 14, 2026, the day arrived that had been awaited since November. The JUICE space probe completed data transmission obtained during 3I Atlas observations from November 2nd to 25th, 2025. Nearly a month of continuous measurements, photometry, spectroscopy, infrared imaging. Terabytes of information were uploaded to European Space Agency servers and became available to the project's science team. Primary analysis began immediately, but they warned, results won't appear before March. Instrument calibration is required, data checking for artifacts, comparison with other sources. But some results leaked unofficially. A source on the JUICE team, requesting anonymity, told journalists, "In high-resolution images taken in mid-November, structures are visible in the coma that are difficult to explain by chaotic gas and dust ejections. Several bright points arranged almost symmetrically around the nucleus. A spiral pattern in the dust tail, too regular for random formation. Localized regions of increased brightness flickering with a period of about 6 hours, possibly related to nucleus rotation, or, the boldest whispered, to activity of something on the surface or inside." Official agency representatives rushed to calm the public. All observed structures, they stated, are consistent with known cometary processes. Symmetrical bright points are jets, gas streams bursting from active regions on the rotating nucleus. The spiral pattern results from the same rotation, when ejections trace curved trajectories in space. Brightness changes are natural modulation of reflected sunlight due to surface inhomogeneity and rotation. Nothing extraordinary, nothing requiring exotic hypotheses. But the statement's tone was defensive, almost irritated, as if the agency was tired of fighting the wave of speculation. On March 1st, a large international group of astronomers, more than 50 authors from 20 countries, published a comprehensive paper on 3I Atlas in Nature Journal. This was a fundamental review of all data collected from the July 1st, 2025 discovery through mid-February 2026, spectra from numerous telescopes, photometry, light curves, chemical analysis, trajectory models, physical parameter estimates. The paper occupied 20 pages of small print plus 40 pages of supplementary materials, tables, graphs, calculations. Conclusions were cautious and balanced. 3I Atlas is an interstellar comet, the third confirmed object of this type after Oumuamua and Comet Borisov. Nucleus diameter about 11.5 kilometers, elongated shape, axial ratio approximately 2:1. Rotation period about 6 hours. Chemical composition anomalous, excess carbon dioxide relative to water, unusual nickel to iron ratio, early water vapor release at great distances from the sun. These features indicate the comet formed in a protoplanetary disk with different conditions than the sun's, possibly around a star with different metal content, at different temperatures and pressures. The comet's age was estimated at 5 to 7 billion years, older than the solar system. This meant 3I Atlas formed in the early galaxy, when star formation was more active, when supernovae enriched the interstellar medium with heavy elements faster than now. The comet carried an imprint of that era, memory of chemical processes that billions of years ago created planetary systems under completely different conditions. Studying such objects, the authors emphasized, provides a unique opportunity to look into the galaxy's past, understand how planet formation conditions changed over cosmological timescales. Regarding the artificial origin hypothesis, the paper rejected it unequivocally. All observed features, the authors wrote, are explained by natural processes. Not one sign requires invoking the hypothesis of intelligent intervention. Red color results from cosmic ray irradiation. Excess carbon dioxide follows from formation near the snowline in the home protoplanetary system. Anomalous metal behavior is possible, nickel-carbonyl formation under specific conditions. Local brightness changes are rotation of an inhomogeneous nucleus and jets. Trajectory coincidence with Earth spacecraft is indeed surprising, but not improbable, given the number of missions flying through the inner solar system. The paper was cited hundreds of times in the first weeks after publication. It became the official scientific position on 3I Atlas, but those who wanted to believe in mystery continued to doubt. Too convenient an explanation, they said. Too many coincidences swept under the rug by statistics and probabilities. Maybe truth is hidden in classified data that didn't make it into the publication. Maybe governments agreed not to reveal the truth to avoid panic. Conspiracy theories, fed not on facts, but on absence of final answers, the space of uncertainty between possibly and certainly. By mid-March, 3I Atlas was more than 600 million kilometers from the Sun, beyond Mars's orbit, approaching the asteroid belt. Apparent magnitude dropped to 15th, beyond amateur telescope capabilities, accessible only to large professional observatories. Activity ceased completely. The coma disappeared. The comet again became just a dark chunk of ice and rock reflecting faint sunlight. Observations became increasingly difficult, required ever longer exposures, ever more precise telescope guiding. On April 15, 2026, Palomar Observatory in California obtained the last clear image of 3I Atlas. The 5-meter Hale telescope, one of the world's largest, pointed its mirrors at a faint point crawling between stars in the constellation Cancer. Exposure lasted 30 minutes. The camera accumulated photons, tearing signal from noise. In the final image, the comet looked like a barely distinguishable dim point, indistinguishable from distant galaxies except for its motion. This was farewell. After this, the comet would go too far, become too dim even for giant telescopes. Humanity was losing it from sight, possibly forever. The astronomer who obtained this last image wrote a short post on social media. "Farewell, wanderer. Thank you for stopping by. Safe travels through the galaxy. Maybe in millions of years, you'll visit another star system, and someone there will also wonder about your origin." The post was quoted thousands of times, became the symbolic conclusion of a story that began on a clear July day in the Chilean Andes when the Atlas telescope first detected a faint speck of light moving along an incredible trajectory. What remained after 3I Atlas? Terabytes of data that will be analyzed for years, dozens of scientific papers, defended dissertations, constructed models, new questions about chemical diversity of protoplanetary disks in the galaxy, confirmation that interstellar objects regularly visit the inner solar system, and perhaps it's worth building specialized missions to intercept them, and also memory of a chance encounter, of how 2 Earth spacecraft heading to completely different targets found themselves at the right time in the right place and touched a mystery that came from beyond our home. Somewhere out there, in the cold and darkness between Mars and Jupiter's orbits, the ancient comet continued its path, frozen, silent, carrying within itself answers to questions that humanity had only begun to formulate. In a year, it will cross Jupiter's orbit, in decades, Neptune's in centuries, it will leave the Oort cloud, and again become an interstellar wanderer, free from stellar gravity, belonging to the entire galaxy, no one's and everyone's simultaneously, and people will remain on their blue planet, gazing into the sky, awaiting the next visitor from beyond the boundary of the known, the next messenger from that abyss that lies between suns. On a May morning in 2026, when gardens bloomed on Earth and people made plans for summer, Comet 3I Atlas crossed an invisible boundary. It was now about 750 million kilometers from the Sun, beyond Jupiter's orbit, in that region of the solar system where cold and darkness reign. Apparent magnitude dropped to 16th, beyond the capabilities of even the largest ground-based telescopes. Only space observatories, Hubble and James Webb, could theoretically detect its faint reflected glow, but time on these instruments was expensive, every minute of observations worth its weight in gold, and spending them on a disappearing point from which all available data had already been obtained seemed wasteful. The comet became invisible, but its influence continued to grow. In June, a team from California Institute of Technology published a detailed analysis of the isotopic composition of ions detected by Europa Clipper on October 31st of the previous year. The ratio of oxygen isotopes, oxygen-16, oxygen-17, and oxygen-18, differed from solar by about 4%. This was more than statistical error, more than could be explained by fractionation in solar wind. The numbers pointed to different origin, to a protoplanetary disk around a star with different heavy element content, possibly a star enriched by products of a nearby supernova. Modeling revealed a surprising thing. If we assume 3I Atlas formed in a red dwarf system, the most common type of star in the galaxy, then the snow line there would be much closer to the star than in the solar system. Red dwarfs are cold, shine dimly, and their habitable zones, regions where liquid water can exist, are located practically right next to the star. In such a system, a comet could form from material enriched in carbon dioxide and depleted in water, which would explain the observed chemical composition. A red dwarf could exist 8, 10, even 12 billion years, longer than the Sun exists, and the comet could have traveled through interstellar space for most of the galaxy's history. The July issue of Science Journal published a provocative paper by a group of planetary scientists from the University of Arizona. They claimed that the distribution of organic molecules in 3I Atlas's coma, methanol, formaldehyde, hydrogen cyanide, hints at the presence of amino acids, although direct spectral confirmation wasn't obtained. If amino acids really were there, it meant life's building blocks travel between stars on interstellar comets, seeding planetary systems with organic molecules necessary for biology's emergence. Panspermia, the ancient hypothesis that life spreads through space, was gaining new arguments. Critics pointed to weak evidence. Indirect signs aren't direct measurements. Models aren't observations. But even the possibility of such interpretation captured imagination. Maybe life on Earth didn't start here? Maybe the first organic molecules from which protobiological systems later assembled arrived on comets from another star system. Maybe somewhere out there, orbiting a distant red dwarf, exists a planet where the same molecules from the same protoplanetary nebula that spawned 3I Atlas assembled into living organisms, evolved, created intelligence. These questions had no answers, but the very fact of asking them showed how one ancient comet changed the boundaries of scientific thinking. The August conference of the International Astronomical Union in Cape Town, South Africa, devoted an entire session to interstellar objects. Astronomers from around the world gathered in a large hall, discussing strategies for detecting and studying future visitors from beyond the solar system. Statistics indicated every 2 to 3 years, an interstellar object larger than 100 meters should pass through the inner regions. Most go unnoticed, pass too far, too dim, move along unfavorable trajectories. But telescope improvements, expansion of sky surveys, new automatic detection systems, all this increases chances of finding such wanderers regularly. The proposal to create a specialized interceptor mission gained new momentum. Several space agencies, NASA, European Space Agency, Japan Aerospace Exploration Agency, began joint concept development, a spacecraft with powerful engines capable of developing high speed in short time, equipped with a set of scientific instruments for detailed study of comets and asteroids. The spacecraft would be stored in near-Earth orbit in a state of readiness, and when telescopes detect a new interstellar object, the team would quickly calculate an intercept trajectory, upload it to the onboard computer, and the probe would launch in pursuit. Implementation timeline was estimated at 10 to 15 years, cost at $3 to $4 billion. Expensive, but not prohibitive for an international project. On a September evening, an amateur astronomer from New Zealand, sorting through archival images taken in April, discovered something strange. On one of the last images of 3I Atlas obtained before the comet became too dim, a barely distinguishable elongation of glow was noticeable, as if the comet had grown a tail again. But this was impossible. At a distance of more than 600 million kilometers from the Sun, temperature is so low that no known volatile substances can sublimate from the surface. Even carbon dioxide under such conditions is harder than rock. Where did the tail come from? The astronomer published the image on a forum, asking colleagues to verify. Several other observers, digging through their archives, found similar signs in images from the same period, faint, barely noticeable, on the edge of detection, but stubbornly repeating. Professional astronomers were skeptical, most likely a processing artifact, background stars, random coincidence. But theorists proposed an explanation. Maybe exothermic chemical reactions continue inside the nucleus, releasing enough heat for slow sublimation of the most volatile components. Carbon monoxide, methane. These substances can sublimate even at temperatures of minus 200 degrees if internal heat warms them from below. Then the comet isn't dead, not completely frozen. Inside, it still flickers the weak fire of ancient processes. On an October morning in 2026, exactly 1 year after the comet passed perihelion, the JUICE team, the European probe to Jupiter's moons, published final analysis of November observations. Data confirmed the presence of structures in the coma. Several bright regions arranged almost symmetrically, and a spiral pattern in the dust tail. But the explanation proved mundane. The comet's nucleus rotated with a period of about 6 hours, and on its surface were 4 to 5 active regions, areas where ice composition or structure differed from the surrounding surface, leading to localized sublimation. Rotation created a pinwheel effect. Jets traced spiral trajectories. No mystery, no artificiality. Just an inhomogeneous comet rotating in space. But for those who wanted to believe in more, these explanations seemed too convenient. 4 to 5 active regions arranged almost symmetrically. Isn't that suspicious? Rotation with a period of exactly 6 hours. Too round a number. Maybe true data is hidden, and they only publish what won't cause panic. Conspiracy theories, muted for several months by scientific publications and official statements, began whispering again on forums and in closed groups. November exercises of the International Asteroid Warning Network, planned back in October 2025, proceeded using 3I Atlas data. From November 27, 2025 to January 27, 2026, 2 months of coordinated observations and analysis, simulating a situation when an unknown object approaches the inner solar system. Astronomers practiced procedures for rapid trajectory determination, risk assessment, information transfer to governments and space agencies. 3I Atlas posed no real threat, but served as an excellent training object, a real interstellar guest with unusual properties. By December 2026, the comet was more than 1 billion kilometers from the Sun, beyond Saturn's orbit, in the cold darkness of the outer solar system. No one saw it anymore. No one observed it. It became just a point in catalogs, a record in databases, an object whose orbit was calculated and entered into computers. In a few years, it will cross Uranus's orbit, then Neptune's. In decades, it will enter the Oort cloud, a scattered collection of trillions of icy bodies at the boundary of the Sun's gravitational influence. In 100, maybe 200 years, it will leave it and again be free. Again will belong to interstellar space. What will remain from the encounter? Hundreds of scientific papers analyzing every aspect of the comet: chemical composition, physical parameters, trajectory, origin. Confirmation that interstellar objects carry information about other planetary systems, other formation conditions, other epochs in the galaxy's history. Impetus for developing new missions, interceptors capable of catching up and studying future visitors in detail, and also memory of that moment when humanity touched mystery, when two spacecraft heading to completely different targets found themselves at the right time in the right place and tasted material from another star system. For most people, 3I Atlas became just news that flashed in the feed and was forgotten in a week. For enthusiasts, a source of theories, debates, endless discussions about whether it was just a comet or something more. For scientists, a precious data source that will be analyzed for years, generating new questions and hypotheses. For space engineers, a lesson about how important it is to be ready for unexpected opportunities, how random coincidence can give a scientific bonus if instruments are ready and the team reacts quickly. Somewhere out there in the cold darkness beyond Saturn's orbit, the ancient wanderer continued its path, silent, frozen, carrying remaining mysteries within. 7 billion years it traveled through the galaxy. Several months it spent near the Sun, allowing people to steal a few grains of knowledge. And now it was returning to the abyss from which it came. Maybe in millions of years, it will visit another star, another civilization, other minds that will also try to solve its secrets. Or it will fly past, unnoticed, through the void between luminaries, keeping in its icy heart memory of times and places that Earth scientists can only dream about. On a March evening in 2027, more than a year after the last reliable observations, a small group of enthusiasts held a virtual meeting dedicated to the memory of 3I Atlas. They gathered not in a real hall, but in digital space. People from different countries, different time zones, united by common interest in the interstellar wanderer that flashed through their lives like a shooting star. They shared memories of those days when the comet was visible in telescopes, when every news about it was discussed with excitement, when it seemed something was about to be revealed that would change everything. Now, more than a year after its disappearance from view, emotions had settled, passions had cooled, leaving quiet nostalgia for a moment of touching mystery. The comet was now somewhere beyond Uranus's orbit, almost 3 billion kilometers from the Sun. No one knew its exact position. The last observations dated from April 2026. Since then, the trajectory was calculated only mathematically, based on known orbital parameters and planetary gravitational influence. Perhaps the comet deviated from the calculated trajectory under weak non-gravitational forces, reactive thrust from sublimation of residual volatiles, solar light pressure on dust particles. But these deviations were so small that no instrument could detect them at such distance. In summer 2027, a monograph appeared, a thick 500-page book published by a university press, collecting all scientific results of 3I Atlas studies. The author collective numbered more than 200 names: astronomers, planetary scientists, chemists, plasma physicists, celestial mechanics specialists. Each chapter was devoted to a separate aspect: orbit, chemical composition, physical characteristics, interaction with solar wind, comparison with other interstellar objects. Appendices contained observation tables, graphs, spectra, photographs. This was a monument to painstaking work, systematization of knowledge obtained during several months of intensive observations. The book was purchased by several hundred specialized libraries worldwide. Several thousand scientists downloaded the digital version. For the general public, it remained unnoticed. Too specialized, too technical, full of formulas and terms inaccessible without specialized education. But for those who devoted their lives to studying small bodies of the solar system, this book became essential, a data source consulted again and again, comparing 3I Atlas with new discoveries, seeking patterns, building theories about the diversity of conditions in protoplanetary disks of distant stars. In autumn 2027, the Interstellar Object Interceptor Mission Project received official approval from the Space Agency Consortium. Budget was approved, $3.5 billion over 15 years. Instrument development, spacecraft construction, launch into near-Earth orbit, maintenance and readiness until detection of a suitable target. The mission was named Hermes, after the ancient Greek god, messenger between worlds. Symbolic, the spacecraft would be humanity's messenger to objects that came from other stellar worlds. Engineers calculated, if an interstellar object is detected at a distance of 3 to 4 astronomical units from the Sun, Hermes could launch and intercept it in several weeks, using powerful ion engines and a gravitational maneuver around Earth or Moon. The spacecraft would fly past the target at a distance of several hundred kilometers, photographing, measuring, analyzing. Maybe it would drop a small probe that would crash into the surface and take samples of ejected material. Maybe it would deploy a spectrometer and analyze coma composition in real time. Everything depends on the specific situation, on trajectory, on object type. But readiness will be there. In winter 2028, astronomers discovered a fourth interstellar object, a small asteroid flying through the inner solar system at 70 kilometers per second. It was dim, just a few tens of meters in diameter, passed far from Earth and planets, showed no signs of activity. Discovery occurred 2 weeks before closest approach to the Sun, too late to organize detailed observations, too late to launch Hermes, which was still being built in factories. Astronomers managed to obtain several spectra, determine approximate composition, rocky, rich in silicates, similar to inner belt asteroids. In a month, it disappeared from view, carrying its secrets back to the interstellar abyss. But this discovery confirmed statistics. Every 2 to 3 years, an interstellar object, sometimes a comet, sometimes an asteroid, sometimes large, sometimes tiny. The galaxy is full of wanderers ejected by gravitational perturbations from their home planetary systems, traveling millions of years through void, randomly passing other stars. The solar system is no exception, no closed fortress. It's a crossroads regularly crossed by visitors from afar. Most unnoticed, some recorded, a few studied. In spring 2030, an astrophysics student from Tokyo, sorting through archival data from the James Webb Space Telescope, discovered something strange. In infrared spectra of 3I Atlas obtained in August 2025, there were weak lines that hadn't been analyzed before. They were considered noise, a calibration artifact. The student applied new processing methods developed for studying exoplanet atmospheres, and the lines became clearer. They corresponded to phosphine molecules, a compound of phosphorus with hydrogen. Phosphine is sometimes detected in gas giant atmospheres, where it forms at high temperatures and pressures. But in a comet, at a distance of 400 million kilometers from the Sun, the student's scientific advisor was skeptical about the find. Careful verification was required, excluding all alternative explanations, confirmation by independent methods. The paper was submitted to a journal, underwent review, received comments, was revised. Publication came out only in autumn 2031, 6 years after the comet's discovery. The title was cautious: Possible Signs of Phosphine in Infrared Spectra of Interstellar Comet 3I Atlas. The scientific community reacted with restraint. Interesting, yes. Requires further study, absolutely. But phosphine isn't a sign of life, not a marker of artificiality, just another chemical anomaly in the long list of unusual features of this comet. Somewhere out there, far beyond Neptune's orbit, more than 6 billion kilometers from the Sun, the ancient wanderer continued its path. Surface temperature dropped to minus 230 degrees Celsius, almost absolute zero. All activity ceased. The last gas molecules ejected during perihelion passage had long dispersed in space. The comet again became what it was for billions of years, a dark ice chunk keeping in its frozen heart memory of the time and place of its birth, a silent witness to the galaxy's history. Summer 2032. The Voyager. One spacecraft, launched back in 1977, continued transmitting weak signals from more than 24 billion kilometers, humanity's most distant artifact. 3I Atlas was about a quarter of that distance, slowly receding, gaining speed under the Sun's gravity, now working for acceleration rather than deceleration. In several decades, the comet will cross the heliopause, the boundary where solar wind yields to interstellar medium, where the Sun's influence ends and true interstellar space begins. Voyager 1 crossed this boundary in 2012. 3I Atlas will cross it around 2070, 40 years after its first visit to the solar system. By that time, only specialists leafing through old catalogs and archives will remember it. For the new generation of astronomers, it will become just one of the interstellar objects that flew through the solar system in the 20s of the 21st century. No special emotions, no mysticism, just data, tables, graphs. Maybe someone will write a historical paper for the 50th anniversary of discovery. Remember the excitement of those days. Debates about origin, hopes for new discoveries. But most will look forward to new objects, new missions, new mysteries. Autumn evening, 2042. An old astronomer who in 2025 was a young graduate student participating in 3I Atlas observations sat in a chair by the window of his country house. Outside it was getting dark. First stars appeared in the sky. He knew, somewhere out there, in the direction of the constellation Pisces, at a distance that light takes half a day to cross, flies an ancient comet, invisible, inaccessible, forgotten by most, but still existing, still carrying memory of the meeting with the Sun, of those months when Earth telescopes followed its every movement, when people argued about its nature, dreamed of mysteries it might keep. The astronomer remembered that July day in 2025 when the discovery message came. Excitement, feverish checking of calculations, understanding. This is an interstellar object, the third in observation history. He remembered autumn nights spent at the telescope, the observatory's cold, the smell of coffee, quiet conversations with colleagues about what might be hidden in data. He remembered the December approach, when it seemed you could reach out and touch the comet, though it was millions of kilometers away. He remembered disappointment when it became clear. There would be no sensation. All anomalies were explained by natural processes. The comet was just a comet. Unusual, yes, but not an alien artifact, not a message, not a sign. And yet, he thought, looking at the darkening sky, the encounter wasn't in vain. Terabytes of data, hundreds of papers, new analysis methods, the Hermes mission preparing for launch in coming years, understanding that interstellar objects aren't rare, that the galaxy is full of wanderers traveling between stars, realization that the solar system isn't isolated, that material from other planetary systems regularly arrives here, mixes with local matter, can seed planets with organics, can influence life's evolution in ways just beginning to be understood. 3I Atlas was a teacher showing humanity that space isn't dead void separated by light years, but a living network of connections where matter, energy, and maybe information travel between stars, creating unity from diversity. Night fell completely. The Milky Way emerged above the horizon, myriads of stars, many having their own planetary systems, many once ejecting comets and asteroids into interstellar space, as the sun ejected objects from the Oort cloud through gravitational perturbations. Somewhere out there, fly wanderers born near our star, carrying molecules of Earth's water, Earth's ice, Earth's organics. In millions of years, they'll reach other star systems, maybe fall on some planets, bring there a particle of Earth and Sun's history. Exchange continues forever. Stars exchange material, like people exchange letters, and in this exchange manifests the galaxy's unity, the connection of everything with everything. The astronomer closed his eyes, letting fatigue take over. In half-sleep, he imagined Comet 3 Atlas, darkening and freezing, rushes through the abyss, carrying memories of the sun's warm light, of that brief period when its icy surface warmed, when gases burst into space, when Earth instruments touched its invisible tails. Maybe in 100 million years, it will meet another star. Maybe again pass perihelion, again sublimate, again someone will observe it and ask the same questions. From where to where, why? The cycle continues. Wanderers travel. Stars are born and die, and matter from which everything is made transitions from form to form, from place to place, carrying memory of the universe's infinite history. Comet 3I Atlas flew through the night, not Earth's night measured in hours, but cosmic night lasting eons. 7 billion years it traveled before. How many more ahead? 10 billion? 20? Until the galaxy disperses, until stars burn out, until the universe's expansion tears the last connections between matter. No one knows. But while the comet exists, while it carries molecules of ancient ice, while it keeps isotopic signatures of a long-extinguished star, it remains a witness, a monument, a messenger from past to future. And in this lies its value, its meaning, its eternal mission. Simply to be, simply to exist, simply to fly through the abyss, connecting with its silent presence what seems separated, showing that distances are surmountable, that time is relative, that everything in the universe is connected by invisible threads of origin and destiny.